Hi, everyone. My name's Heather Adkins, and I'm a Senior Director of Security Engineering at Google. And I'm here today to talk a little bit about building secure and reliable systems. Thank you to RSA for having me. Thank you for all of you for joining in. I'm here to answer questions throughout, so you can drop questions into the chat box, and I'll try to answer your questions as we go. So I'd like to start today by pondering some of the following questions. Can a system ever be fundamentally secure if it's not reliable? And similarly, can it be reliable if it's not secure? Now, if you think about the way complex systems are designed, whether they're airplanes or automobiles, a fundamental principle is to make sure that they run and execute under duress reliably over long periods of time. Similarly, we expect them to be safe. Not only do we not only to run safely every day, but to protect us in the event of an accident. And this is not unlike modern computing systems and large-scale services that we use online, like YouTube and Gmail, perhaps Netflix and Zoom. These are services we've come to really rely on, especially during the pandemic. They've allowed us to connect with people all over the world and get stuff done while we're working remotely. So imagine if these services weren't reliable or secure. For example, if Zoom was reliably running during a classroom session, but a lurker constantly Zoom bombed it. Or if your access to Gmail is really fast and stores lots of data reliably, but your email is constantly being read by hackers because they guessed your password. And in reality, we as developers have long relied on principles of reliability as cornerstones in any of our designs. If a system doesn't run, then it's not a system. But increasingly, we're seeing the rise in this principle of security and its close counterpart, privacy, as being similarly mandatory. So what I'd like to discuss today are some new ways we should be thinking about resiliency in our systems based on how they're architected and designed. And these are the ways we've thought about how to make Google really resilient over time. And this is an increasingly important topic. Every day we see new headlines about companies that we rely on being compromised. Let's just take the example of supply chain attacks, which is very front and center right now. Supply chain attacks, very simply put, are attacks on technology companies that build the software and hardware we rely on and that we integrate into our environments. These are tools we use to design software and hardware, to compile, test, deploy software. Even the tools we use to verify that software and hardware is in and of itself reliable and secure. And these technologies and the companies that build them, we're all at risk. And attackers know how important they are to us and how they can be leveraged to attack others. Now, if you're new to the field, you may not realize that these have been going on for some time. I put a quick timeline together, as you can see. It's not complete by any means. Those of you in the know who will probably spot some things missing, but it does demonstrate that we've had some challenges in this space for a very, very long time. You might even wonder, if we've known this is a risk for a long time, why does it keep happening? I would posit it's because as an industry, we haven't really gotten down to earth serious about how our systems need to be built, how our networks need to be constructed, and how all of these ecosystems fit tightly together. And we haven't made that hard choice to change how we teach practitioners better ways to do things. So the method I would propose is that we start to view these systems as having interconnected, interlinked properties of reliability and security, and that everyone who builds, maintains, and deploys them thinks of these things as existing not only by default, but as inherently necessary. And one reason I like this framing so much is that reliability concepts are so familiar to developers. And these concepts are often more approachable than some of our complex security topics have been over the many years we've been talking about this. At a high level, what does this really mean? What am I talking about? It means we need to rethink entirely the way we build systems and the way we approach designing things. In effect, we need to reshape our ecosystems. Now, I'm fond of saying that modern computing systems are a bit like fish without scales. Scales help keep the salt water out, or gills. Gills help fish consume oxygen in the water. Well, modern computing systems are a bit like fish that have not adapted to living in the ocean. Modern computing systems have no resiliency on the internet. That is the ecosystem that they live in by default. We need to start building these systems differently and reshape the ecosystem they live in order to avoid the kinds of problems we are seeing with the software supply chain every single day. But practically, what does this mean practically? Let's walk through 3 examples I pulled out. There are so many others, but I picked these because we've walked this journey at Google and because they're hot topics that I hear practitioners discussing all the time. The first example I'd like to use is around enterprise architectures. That is the kinds of networks that we build for the companies we all work for. Now, when most practitioners are learning about enterprise network architectures, they're doing so using curricula that we've been teaching in the same way for many, many years. For example, right now, if you're going through a certification, let's take the CompTIA Network Plus cert. You'll learn about the TCP/IP stack and what Ethernet is, and they teach network segmentation as a security feature, which is great. I also did a quick survey through the academic courses online at the moment. During the pandemic, all of their syllabuses are online, which is really great. So let's take a computer networking class at Stanford that they're teaching right now. They're teaching all of the same basics and even some advanced topics like software-defined networking. But at a high level, for almost 30 years, most of us are taught a network architecture principle that results in networks like the one you see on this slide. Here we have the internet, which stands to reason is relatively untrusted. And then there's usually a connection from that, an internet connection into your private network, such as your company's enterprise network. And then there are people who are mobile. Maybe they usually travel for business or occasionally work from home. And very recently, we've also been seeing the rise of software as a service and corporate infrastructure moving into cloud computing environments. But surprisingly, one thing that hasn't become very common is the way people work remotely. In fact, I've met many enterprises who move to the cloud, but still require their employees to connect into the cloud-based services through corporate VPN, through the trusted corporate network. And I often call this the castle model, where we assume everything inside that trusted network is safe and everything outside the castle is not. This castle model presents us with a number of problems. Let's talk first about reliability. And again, I'll use the remote worker as the core of my argument here. I think it's familiar to many people because COVID-19 has really brought this front and center. First off, VPNs don't scale very well. And if you're in a company that's made this transition to work from home during COVID-19, you've probably seen this firsthand. Systems designed for people to occasionally work from home began to fall over with the sudden traffic when everyone was required to be remote. And if you've also ever tried to work on an airplane using a VPN, you've probably experienced frequent drops or actually just the complete inability for the VPN negotiation to happen. And this is because VPN connections are typically full tunnel. The technologies behind them, like IPsec, are really high cost. And from a network traffic perspective, they're not very efficient. And finally, all this service degradation around VPN disconnects and reliability issues leads to productivity loss. And productivity loss means revenue loss. On the other hand, with security, unless you're very, very diligent and very careful, these kind of remote work VPN architectures start to introduce more security issues than they solve. First, you end up with roaming devices that you don't necessarily control. A lot of companies don't restrict access to strongly managed, verified devices. Even Google, before it took its journey to rethink this over 10 years ago, lots of people connected over VPN with their personal systems. And many companies, even still today, have a BYOD program where you can use any system to do it. And goodness knows what's going on those systems. VPNs are also often used to grant broadly privileged access. They are designed to be tunnels for all traffic between two highly trusted places. And this means that if any threat is introduced into that roaming device, children using them for remote school, or unfortunately, as we are increasingly seeing, spousal abuse at home, attackers can get onto these machines and then laterally move from the VPN connection into more sensitive spaces of your network. And this is not ideal. And finally, when things don't go well, if you start throwing up roadblocks or start reducing access, users get creative. I've known many users who have worked around our security controls or tried to, just in order to get stuff done. So you can see here that we have both reliability and security problems with this very traditional enterprise network architecture that we teach practitioners in their training. And we want to do differently. We would all be right to ask, what could this look like to be better? How could we reshape this ecosystem? Well, Google started doing this back in 2011 with the goal of doing just that. And you often hear this called zero trust networking in some circles. At Google, we pioneered this architecture and we've called this Beyond Corp. Beyond Corp being beyond the old corp or beyond the enterprise that we used to know. The premise here is that the once trusted corporate network is no longer trusted. In fact, working inside a Google building is the same as if you were working inside the Starbucks, okay? First, every device has to prove itself is safe, whether it's in that building or whether it's here at home where I am right now. A series of checks happen using what we call the trust decision pipeline that allow the device to assert its trustworthiness. This could be because the machine has a certificate that we've given it, but we'll also use other factors like, is it the right patch level? Has the user authenticated using a strong authenticator like a security key? Or are they even working at the right time of day that we would expect them to be? Second, we leverage the fact that most enterprise services at this point are web-based. Productivity apps like Gmail or Google Docs, filing expense reports, accessing HR systems. This is all facilitated today by the web browser, which is increasingly the most important software in the ecosystem. And all of this means that we can begin to narrow down what traffic needs to be trusted and to come from these trusted devices. Now, I'm simplifying here a bit for time, but effectively what we're saying is that we do strong verification of the machine and the user before allowing any SSL connection to our enterprise cloud services. There's no VPN. Everything is done over the internet using SSL. The effect here is clear for both reliability and security. Instead of the heavyweight VPN for connections into corporate services, we rely on the strength of the more performant SSL. And by designing the network in this way, at any time, we can make the workforce mobile. The solution even works on airplanes without disruptive VPN software, configuration problems, protocol issues with routers and firewalls. It just works as soon as you open the machine. And it also has a lot of benefits for security because we have confidence in the devices that are accessing the cloud services. We know who the employees are. We know that their devices are trustworthy. Also, and one of the best benefits we've gotten that wasn't immediate in our design 10 years ago, but we have seen be very successful throughout, is that if the attacker does happen to get control of that roaming device, they're trapped. That's all they get. They can't use this connection to make remote Windows RPC calls into the Active Directory environment. They can't SSH into the company's financial server. There's no trusted tunnel back to a highly privileged network or a set of highly privileged systems. Now, this isn't foolproof, but our studies have shown that it does slow attackers down, it slows our red teams down. And more importantly, it gives us a leg up during incident response to get to the attacker sooner while they're trying to figure out what ecosystem they're operating in. So you can see that by rethinking the way the enterprise architecture works, we've actually solved a lot of problems about reliability and security together. And we can solve these challenges together at the same time in a way that the practitioners in the field who are implementing the systems can also appreciate using the domain that they're most familiar with. Let's shift topics to my second example around application development. And this is a really vast topic. So to give us some focus, we might actually consider web application development for our conversation. I did a quick survey. You'll see a theme here. I did a quick survey of professional training, certificates, academic studies, and there are a wide variety of approaches that are taken to teaching developers how to build not just code, but systems that code runs on. And there are two pretty popular models. There are others, but I'll talk about these two. The first is the three-tier architecture. And when I first entered the industry 20 years ago, the three-tier model was the one talked about the most. In fact, before I joined Google many, many years ago, I used to run the large-scale mail system for Excite.com, which was when webmail was still very, very new. And our architecture mostly fit into this model. And the second model that we've seen become very, very popular because it's open source and very flexible is the LAMP stack. Now, LAMP stands for Linux, Apache, MySQL, and PHP. We also use the P to mean Perl and Python, whatever scripting language you're using to create the applications. Again, there are other stacks, but let's just talk about these two for a moment. Now, these models provide a basic engine for someone who wants to design, implement, and maintain a web application, such as an e-commerce website. And LAMP is particularly attractive because it's all open source. There is reasonably good documentation, a very strong community, and training that you can get. It's also very quick to deploy on all the big cloud providers. You can quickly develop and deploy a LAMP stack in any of the big cloud environments at this point. And you can even do it on your home Linux system. You can do it on a laptop so that you can run an e-commerce application while you're on an airplane. Nobody else will be able to use it, but you will. You can see there's a lot of convenience in having quick, easy access to technology that just works. And this is the promise of open source, and it's great for many reasons. But it does come with some downsides. Any developer that has launched a single LAMP stack instance, for example, for an online service begins to notice the issues immediately. First, reliability. By default, there's no load balancing between multiple servers, which means that if you have too much traffic, you can't distribute the load. You find yourself having to add another server and another one, and then find a solution for load balancing, and you can kind of see where this is going. Similarly, if you have an errant process or a bug in your code that leads to an expensive database query, maybe it overloads the database, your application queries the database too often, the web app has lots of hanging open connections, it starts to become overloaded. This is all expounded if you're running the whole LAMP stack on just one single machine. And when all of this complexity is going on and your app is crashing, you don't really know which module is broken. You don't really know where to start your debugging. Everything's broken all at the same time. And keep in mind that there are solutions in the space to help solve this. And I don't want to downplay the importance of those. Common modules, networking hardware that provides load balancing and allows you to distribute your apps and do replication. There are certainly solutions for this, but they're strangely not as straightforward in default as we'd like. On the security front, this architecture has no boundaries built in by default. If you're running a LAMP stack on a single machine, or even if you've distributed across several machines and sites for, say Apache for the web server and MySQL for the database, actually the way that these are administered is that people just set up SSH between the hosts. And your MySQL connection allows you to query any data over it at any time as long as you have the credentials. So an attacker working in this environment, perhaps after exploiting a vulnerability in your web application, suddenly not just has access to that, but suddenly has access to everything because everything is so closely tied together and the privileges are broadly shared. And this is the way most systems administrators get introduced to security. Is they find that they've suddenly been hacked by a vulnerability in their infrastructure, and suddenly the attacker has access to everything. And that's how I became a security engineer. I was a sysadmin who got hacked. I think we'd like to think about this differently. I would hope in 10 years, we're no longer talking about this problem I've described. And one of the solutions to this, it's not the only one, but one of the solutions is to begin thinking differently and no longer teaching the basic architecture I've described, but instead encouraging people to use these technologies, Linux, Apache, MySQL, Python, hopefully over PHP, is to use modern architecture design from the very beginning to put these pieces together in a different way that becomes the best practice. And a prevalent example of this is using microservices as a concept. Microservices segment elements of an application into smaller components, creates boundaries around them, and allows the components to operate in a container environment or sandbox that provides that boundary for you. And then in order to work together, the different components have to speak over predefined data flows, APIs, RPCs that can be authenticated in strong ways and in predictable ways. And by doing this container isolation plus data flow model, we're able to control the reliability and security properties of the system just a bit more carefully. I grabbed an example here from the Google Cloud migration documentation. This is not a Google talk. I am going to use some examples from there, but you can find similar examples in a cloud of your choice. But here we have a relatively basic monolithic application. You can see here in the diagram that you have some app servers. Perhaps these are web servers for a commerce website. And built into the application there, you might do everything from accepting the HTTPS connection or allowing the user to do a product search, maintain a web cart, maybe even go through the whole process of purchasing what's in their web cart. So these single app servers tend to do many things. You also have a cache server and a search database, a primary database and replicas. This is actually a fairly complex web app, but you can see here the monolithic nature of that application server layer in particular. But the commonality here is that there are very few boundaries. And because of this, these systems often have highly privileged access to one another. Typically, the admins can SSH between them. You can connect from the front ends to the database with a highly privileged SQL connection. And they're also highly dependent on the performance of one another. Any issue with one becomes an issue with all. But what might this look like if we consider a more modern approach to the architecture? And again, here, this example comes to us from the cloud migration documentation. This is what your architecture might look like if you decided to redesign it. And it takes, the most important thing that we're doing here is that we're taking that monolithic application layer and breaking it down into different functions. And each function then goes into a container. In this case, it's a Kubernetes container, which allows you to take, say, the product search or the web cart or the purchase process, break them down into a smaller app, and then put them inside a container all on their own, which we then call a microservice. Each of them would then connect to other resources. So instead of MySQL, perhaps you'd use Cloud SQL and access the data through an API or an RPC interface instead of the very broad SQL connection. This allows us to better control what kinds of data can be accessed, and we can put really granular permissions on that access so that it's more heavily restricted. Separately, one of your microservices might need to store metadata. Let's say that your product search feature needs to quickly retrieve data for search. You always want that to be quite fast. We've learned that over time. So perhaps instead of a really heavy SQL database, you put this in a quick retrieval system like Cloud Firestore. And so you can see in doing this that we've broken the application down into smaller components. And as they speak to each other, they're speaking over ABIs and RPCs. This makes the application a bit more complex. So microservices are somewhat controversial and they need to be balanced for too much complexity. We know that too much complexity leads to worse security outcomes, actually. But what we've gained here are some very powerful boundaries and failure domains. And this benefits security and reliability in multiple ways. For one, if one of your microservices go down, let's say that you have a catastrophic failure of your product search feature. If that microservice goes down, it won't necessarily bring the others down because you've broken it out. Yes, your website will be a little buggy for a bit, but people could still check out and they could still click around your website. It's also easier to diagnose if that component is failing. debugging becomes more straightforward because you can see within that container and that failure domain that that's the domain that's failing, and it's quite easy to see. This also benefits security. An attacker overtaking any one of your microservices means that they're contained within that environment. They won't necessarily be able to compromise everything else. Secondly, the inherent reliability properties of configuring and running microservices in modern cloud environments means that breach recovery is much more straightforward. And typically, you have to set up the configuration ahead of time. It gets stored in the cloud as a configuration. Your data storage solutions are pre-configured. And all of this is highly reliable in and of itself by design. So should an attacker gain control of this environment and you have to rebuild, a lot of that setup work is saved. And I've seen customers who get compromised be able to redeploy new environments in a matter of minutes instead of the heavy work that we typically have to do in these more traditional environments. Now, I've prepared a really simplistic picture here. And for those of you who have actually done this migration, you know it's very, very difficult. But I've simplified it for a reason. It's because when we are taught application design as developers, we are taught using very simplistic examples. I would advocate that when we need simplistic examples, these are the examples we use instead. And in fact, that we begin to advocate as we build more complex applications in our work that look like these simple examples. It's a way of changing the conversation within our own ecosystem and our community. There's a bonus because I do imagine this sounds really hard. And sometimes the light at the end of the tunnel is very difficult to see. So let's just talk about mobile phone operating systems for the slightest moment, okay? Every day, new developers are being trained to use the software development kits for mobile phone apps. And they're doing so using frameworks that capture the inherent properties of what I've just discussed, this idea of app isolation, where the components of the systems don't have default access. Each app runs in a container, and you have to apply for permission to access data outside of the container. Now, you as a user on your phone see this in the form of allow and deny permission prompts, right? As a developer, the developer doesn't really have to do anything to get all of these benefits. The framework that is inherent in the operating system does it for you. So we've been able to abstract a lot of that complexity away from the developer and the user. Now, getting to this point with mobile phone operating systems has been a decade-long journey, whether you're talking about the Android ecosystem or the Apple ecosystem, or even the Chrome ecosystem. We have not, it has not been an easy journey for us, but it's been a really beneficial one because we are really getting the benefits of having rethought the way operating systems work and apps work. So just a quick example here on how we can really make change over the long term. And finally, my third example, I want to talk a little bit about managing infrastructure. And again, I did a quick look through all the training materials and the certification programs for setting up and managing infrastructure. And strikingly, despite the fact that we've been doing this for many decades, it's still super common for new administrators, site reliability engineers, network administrators, and so on, to be taught that to manage a system, you have to log into them with really high levels of privilege, a root account, an administrator account, or having enable access on a router. And these broad privileges make you feel really cool about yourself, but they have immense power. I remember being root at Google and it felt really good. But I look back on it now and I cringe with how much power that those accounts had. You can upgrade software and change configurations, do debugging. That's all great. You can also accidentally delete the file system or corrupt data, or even bring the system down. Any Unix administrator who's been in their field long enough has accidentally deleted the root file system at least once. I am guilty of that as well. And it's not just about you. Anything that you can do, an attacker who's hijacked your account can do as well. And so if you've been phished, if you have malware on your machine, or you've come to any other catastrophic outcome, this can be really dangerous for the whole ecosystem that you're administering. And in a study that Google performed on its own SREs, and we spoke publicly about this in 2019, we estimate that there's a 0.01% chance that any SRE at Google could make a mistake. And with a team of about 1,400 SREs, that means there's a 75% chance of a major outage every year. And that a major outage might take search down or Gmail down, and nobody wants that. Now, mind you, this isn't a massive infrastructure the size of ours, but you can extrapolate this into your own environment that it will happen eventually. And again, I mentioned that anything that you have, an attacker can get too. Okay, and so we realized at Google quite a while ago that really what we wanted was to stop people from having root, administrator, broadly privileged access, and that we wanted to reshape the way we thought about this and the way that developers and SREs interact with our key production systems. And what I'm going to describe here doesn't apply to every system at Google, but we've been able to apply it to the most important ones that are fundamental to our infrastructure. And this is now the default, such that every change made in our production system is validated either by automation or pre-validated by software, or we have two-party systems. And as a final result, break glass mechanisms. And I'll talk about what that means. But it effectively means that humans are no longer directly logging into these systems. If they do, it's a rare event. And this is a concept we call zero-touch prod, and it has massive implications for security and reliability. Here's one approach for how we've solved this. And this example comes from a book we wrote, which I'll reference at the end if you're interested in reading. Instead of the SREs and developers logging directly into systems, we've built a set of command line tools that send RPC calls to a proxy. And this proxy only permits certain actions against the system to be made. This is common actions like starting and stopping a service, deploying a new version of the service. In the example you see here, the tool will allow you to kill a Borg job, which is our nickname for our cluster management infrastructure, the equivalent of logging into a Unix system and killing an Apache process effectively. The proxy serves several purposes. Its job is to authenticate every request made. And we do this with a highly secure two-factor solution called security keys. And this means you can no longer log in directly as root and do 100 actions with one authentication. You have to successfully, validly authenticate for every sensitive action that you want to take. We also leverage the proxy to enforce two-party approvals. That means if you want to do something extraordinarily sensitive, we can require a peer to review what you're going to do to see if you're making a mistake. The proxy also lets us document any bug numbers, change management IDs, anything else associated with the action, meaning that we have a really good documentation and attribution on every change made in our production environment. The proxy can also do validation checks to see if you've made any errors. Maybe you've put an invalid path in, or you've got overbroad scoping and you're going to touch too many machines that you didn't mean to. Common issues such as this that we've often seen lead to mistakes, and we can program these over time as we learn about new kinds of mistakes that we make. And you do still have a full login option if you are in the right kind of role, but it's really meant as a last resort in rare circumstances. And they're small enough in number that every time it happens, we can carefully audit that manually. And the benefits, I would think, are fairly evident. Mistakes are captured before they're executed, and we have great records on how it happened and who approved it. And on the security front, if you're an attacker operating in this environment, it's actually really tough to do anything with these accounts. If you can imagine, you've gotten onto an SRE's workstation, your only interface into production really is this proxy. And it's not perfect because we know from our red teams that it can be bypassed, but we usually see that. It usually takes the attacker longer to figure out how to work around. We can slow them down before they get to anything. And in some cases, they're fully prevented. Things like security keys, two-party authorization, really create strong barriers for security. Finally, coming all the way back to our topic of supply chain, imagine if we had these 3 examples deployed at a company that develops software. If we were using Zero Trust networks for SREs and developers who are working, we would trust their devices. We would know who they are at any time and that they are safe to use. Imagine your build repository, your build process, your delivery pipelines. They could all be architected as microservices in and of themselves with strong boundary protections. And all of this could be managed by SREs who practice zero-touch prod techniques. And an attacker in this environment would have to work significantly different than those that attacked SolarWinds, Microsoft, and others recently. And in fact, many of the techniques they used for lateral movement and privilege escalation just simply wouldn't work here. And this is the architecture we use at Google. And we have witnessed the difficulties that our red teams face on a regular basis. And it really does give the blue team quite a leg up on things. So in summary, by reshaping the ecosystem and working very differently, we can begin to move the conversation forward on how we solve some of these systematic issues that we've been observing for so long. So how might you get started? This is always the big question because it sounds really hard. I would recommend starting small. Maybe next week you do a quick study. How many outages have you had in your environment, or sort of how many attackers have gotten into your environment, and maybe try to identify where zero-touch prod would have worked. If you'd had a proxy in your environment, mitigating, or rather remediating some of your actions, would that have actually prevented the situation? I think a lot of leadership teams really value data. And so having data is an important thing to gather. Secondly, maybe you'll have a workshop with your colleagues to discuss maybe one of your monolithic services that isn't really working very well. And maybe play around with the idea of a redesign. What would that look like? Don't get too bogged down in is it feasible? I think it's important to have the conversation, even if your outcomes are failures. If you fail enough times, you'll succeed one day. And maybe try thinking a little bit about training for the long term. You don't have to necessarily go out and change everything right away, but you can start helping the teams you work with rethink some of these ideas about how you could reshape your ecosystem. And maybe you're stuck with the systems you have today, but maybe the next one your teams build will look different than the ones you have today. Re-architecting is always hard, but when you can get in at the ground zero and start reshaping from the beginning, that's really great. And then I'll give you a bonus. Maybe host a book club. I can recommend a great book. This is a book that myself and about 100 Googlers put together that describes all of our experiences and recommendations for thinking about building secure and reliable systems and how you can move forward. We use this internally and read a chapter about every 2 weeks. It's great to get together and just talk through some of the concepts in there. And I know a lot of teams have been very successful at that. And then if you have any questions or any of these 3 examples I gave you are interesting at all, here's some additional resources. You can take a photo of this or a screenshot, and these might provide a little bit more insight into how to do some of these things. I think microservices, especially as a concept, there's some great resources going back several decades, but also some really great books that have been written recently that came out in 2020 during the pandemic, particularly on container security and the fundamentals of software architecture. And I find these to be really, really great resources. So with that, I want to thank the RSA team so much, and to thank all of you for joining me here for chat. And I wish you all of the best. Thank you.